In the last lecture, we looked at computations of class groups of quadratic fields. Today, I will start by computations of quadratic fields in cubic fields, class groups in cubic fields. And if there is time at the end, we will also look at one example of a quadratic number field with a somewhat large class number. Okay, so here are some examples. So, K is cube root of cube root of 2, right. So, what is n here? N is of course 3, and what is R1 here? R1 is 1 and R2 is 1. So, this number field has one real embedding, which is you take cube root of real cube root of 2, and it has two pairs of complex embeddings. So, one complex place, right, and so Minkowski bound for this becomes this is 3 factorial by 3 cubed times 4 by pi into. So, what is the discriminant of this? I think we did compute this at we computed discriminants for real quadratic so pure cubic fields, sorry, and this turns out to be right 27 times 2 square. So, this so this is 27 times 4, which is 108. So, square root of 108, right. And if you compute sort of what this is, then this turns out to be lots of large numbers involved, but I do not know. So, 8 by 9 times pi into, let us say, if I approximate this by 11. So, 88 by 9 which is less than 10, and 10 by maybe that is a bad idea to approximate it by 11. So, let me keep it as it is and use the computations that I have in my notes, and this turns out to be less than 3. Okay. So, the only prime that I kind of care about is primes dividing 2. So, CLK is generated by primes dividing 2. And so, what is 2 times OK, right. So, that is what we are interested in. And you see 2 times OK, you do not even have to do very much. This is cube root of 2 cubed, right. And so, this is a prime ideal, cube root of 2, this ideal is a prime ideal, right, and its principal. Okay. So, hence the class group of K is trivial, right. So, that is very nice. So, let us look at another example of this kind. So, you look at cube root of 3, right. So, again n is equal to 3, R1 is equal to 1, R2 is equal to 1, and in this case again the discriminant turns out to be 27 into 3 square. So, 3 square into 27, which is 3 to the 5, which is 81 into 3, which is 243, right. Okay. So, Minkowski bound in this case is equal to 3 factorial by 3 cubed times 4 by pi into square root of 243. So, that is 9 times square root of 3. Yeah, maybe I can do this thing. So, 8 by 9 times pi into 9 times square root of 3, and so 9 which is 8 times square root of 3 by pi, again maybe not such a good idea. So, this turns out to be less than about 4.5. Yeah. So, it is certainly less than 5, right. So, I have to look at what 2 OK is and what 3 times OK is, and the polynomial that I am interested in is x cube minus 3, right. So, x cube minus 3 is congruent to x cube minus 1 mod mod 2, which you can factorize as x minus 1 into x square plus x plus 1 mod 2. And the second factor, the quadratic factor, turns out to be reducible. It has no root mod 2. So, this is p 2 times p 2 prime. So, one of them has residue degree 1 and the other one has residue degree 2, right. And then this turns out to be cube root of 3 square cube, right. Okay. All right. So, so CL of k is generated by the class of P2. Right? The class of P3 is of course trivial, and so I want to know whether yeah. So, what is norm of P2? Norm of P2 is plus minus, I mean it's the ideal generated by this thing, right. So, it's ideal generated by 2, and norm of P2 prime, this is ideal generated by 4, right. So, we want to know whether any of these are principal. If one of them is principal, the other one will be principal as well, right. And so, what I am going to say is, yeah, you consider minus 1 plus cube root of 3, right. So, what is norm of alpha? So, one way to find this is you take alpha plus 1 cube, this is 3, and so you get alpha cubed plus 3 alpha square plus 3 alpha minus 2 is equal to 0. So, norm of alpha is right. So, norm of alpha is the ideal generated by norm of alpha is the ideal generated by 2, right. And yeah, and so so P2 is the ideal generated by alpha. So, hence the class of P2 is trivial, and so hence the ideal class group of K is the trivial group. Okay. All right. So, we have seen two purely cubic fields with trivial ideal class groups, and the reason I am not going to give you compute for you an example of a purely cubic field with higher class number, and so I am just going to state the fact that if you take cube root of 7, then this is isomorphic to Z mod 3Z. And the reason I am not going to do this for you is kind of simple, and you can imagine why I would be doing this is if you look at the group of units in the ring of integers of such a number field, then it is again infinite, and to show that something is not principal, when the group of units is infinite is highly non-trivial, as we saw in the case of real quadratic fields, right. And so, these computations turn out to be really long and yeah, tedious. So, the other example is, if you look at this, then again this is non-trivial, it is z mod 2 z. Okay. But let me give you a example of a cubic field with class number with non-trivial class number. And so, let me look at the following example. Let us see how much of this we can do. So, K is Q alpha, where alpha cubed minus alpha minus 9 is equal to 0, right. So, I am looking at x cube minus x minus 9 is equal to 0, right. And so, why is this polynomial irreducible? So, P x is congruent to x cube plus x plus 1 mod 2, and this is irreducible mod 2. Hence, P x is irreducible over z, and hence by Gauss's lemma, hence over Q, right. Okay. So, this is a cubic field. So, degree of K, so n, which is degree of K over Q, is 3, right. Yeah, all right. Now, if you you can ask whether, so what is R1 and R2 in this case? So, what are how many real roots and how many non-real roots does this polynomial have? And yeah, so how do you find out how many real roots and how many non-real roots does this have? So, what you do is you okay, so alpha cube minus alpha minus 9 is less than 0 if alpha is less than 0, for example, and alpha cube minus alpha minus 9 is bigger than 0 if alpha is bigger than 3. So, my claim is that P x equal to 0 has only one real root. Okay, maybe I'll prove this claim a little bit later. So, let me sort of assume the claim and then say R1 is 1 and R2 is 1. And so, what is the discriminant of this? So, if you look at delta squared of 1 alpha alpha square, this turns out to be discriminant of this polynomial x cubed minus x minus 9, which turns out to be minus 2183 if you do the computations, right. Then yeah, and this is square free. Okay. So, hence this is equal to delta square 1 alpha alpha square, and OK is z alpha. Okay. All right. So, this is minus 2183. Okay. And so, if you compute what the Minkowski bound is, then this turns out to be 3 factorial by 3 to the 3 into 4 by pi into square root of 2183. Okay, maybe yeah. Now there is one more way of doing the yeah. maybe I will not need this claim. There is one more way of deducing that. So R1 is 1 and R2 is 1 without the above claim. So claim, and this is done as follows. So you see that sine of dk is equal to -1 to the R2, and so R2 is odd, and the only way this can happen is, hence R2 is 1 and R1 is 1. Okay, so Minkowski bound is then you can show that this is less than 14. Okay. So, I need to compute what p times OK is in the following cases. So, p, right, I look at x cube minus x minus 9 mod p. So, if p is 2, then this is irreducible as we just saw. So, this is 2 OK is a prime, right. If it is 3, then you see it factorizes as x into x square minus 1. So, x minus 1 into x plus 1, right. And so, this is P3, P3 prime and P3 prime double prime. If you take 5, then this factorizes as x minus 3 into x square plus 3x plus 3, and so this is P5 into P5 prime. 7, this is irreducible, you can check it, and so it is just 7 times OK. 11, this factorizes as x minus 8 into x square plus 8x plus 8, and so again it is P11 prime. And 13, this is irreducible, so this is 13 OK. Okay. All right. So, the only thing that are kind of the only primes that are relevant for us are 3, 7, not 7, sorry, 3, 5 and 11, right. And so, we want to know what happens in those cases. So, I will make another table now. So, I will make another table. If I take norm of a plus alpha, then this turns out to be or the mod of this, then this turns out to be a cubed minus a plus 9. Okay. So, this is just some computation that you do, and so I am going to make another table where I am going to put a here and a cube minus a plus 9 here, and so if I put a equal to 0, I get 3 square. If I put a equal to 1, I again get 3 square. If I put a equal to minus 1, then I again get 3 square. If I put a equal to 2, then I get 3 times 5. If I put a equal to minus 2, then I get 3, right. If I put a equal to 3, I get 3 times 11. So, 3, 5 and 11, they are all kind of appearing. So, this tells me a equal to minus 2 tells me that P3 is 1, right, and hence yeah. So, P3 is okay, maybe this is not how I would I want to do this. Okay, let me do the following. So, when I put a equal to 0, I get alpha is P3 square, and when I put a equal to 1, I get alpha plus 1 equal to P3 prime square, right. These two are of course different primes, because if this is also P3 square, then alpha and alpha plus 1, they both belong to P3 square, which means that 1 belongs to P3 square, and that does not happen. So, they are different primes, and you see alpha minus 1 is also square of a prime above 3. So, it has to be this of this form, right. Okay. And so, when you put things this way, you get alpha minus 2, which is congruent to alpha plus 1, which is congruent to 0 mod P3 prime. And so, P3 prime is the ideal generated by alpha minus 2, because they as norm of alpha minus 2, this thing is same as mod 3, right. Okay. So, P3 prime has class 1, okay. And if you look at what alpha plus 2 is, then this turns out to be P3 double prime times P5, and alpha plus 3, this turns out to be P3 times P11, okay. And so P5 and P11, they kind of are taken care of by P3 and P3 prime and P3 double prime, and P3 prime is anyway 1. So, P3 and P3 double prime generate the class group, right. That is what we have proven up to this point, right. And we know that P3 and P3 double prime is also 1, right, because when you take the product with P2 prime P3 prime, then you get the ideal generated by 3, and so this is also 1, which means that we just have to find so CL of K is generated by P3. That is how the numberings are rigged. Now, alpha is P3 square. So, which means that P3 square is 1, right. And so, we just want to know whether P3 is principal. So, is P3 principal, right. And so, let us say P3 is generated by some beta is in Z alpha. Then what do? We get beta square is the ideal generated by P3 square is the ideal P3 square, which is also generated by alpha, right. And so, we get that alpha times u is beta square for some u in OK cross, right. And we want to show that this does not happen, right. We want to show that this does not happen. Okay, and this is kind of a very involved computation. So, this is difficult to show, difficult and lengthy, and let us not do that here at all. But so you just take this as a fact that so to prove that alpha times u is not equal to beta square for any u in OK cross and beta in OK. Okay. So, anyway, so this means that P3 is not principal, hence the ideal class group of K is isomorphic to Z mod 2Z. This is exactly the kind of thing that I was saying, that if you work with cubic fields, then the group of units is infinite, and when the group of units is infinite, you to show something is to show some ideal is not principal usually turns out to be a very difficult task. All right. So that brings us to end of our computations, and so I hope you have seen enough of these computations that you will be able to compute ideal class groups and apply all these tricks and methods that we have learnt in the course to compute ideal class groups, discriminants, rings of integers, etc. Thank you.